Welcome back to Physics 30. This is part 2 of the MP1.6 region. So we discussed this little relationship here that we've looked at in that online simulation that we did. So the least tightly held electrons will be emitted with the most kinetic energy, because if we think of it, if I use just a small amount of this light beam to eject an electron, the more energy will exist in moving it across the plate gap. But if an electron takes a large amount of energy to get dislodged, only there's a little bit of energy left over, so it'll have a smaller kinetic energy. So the least tightly will have the most kinetic energy, and we can call that the KE max, the maximum kinetic energy, in which case W in this equation becomes the work function, and kinetic energy max becomes this. So if we look at the absolute minimum energy that I need to remove an electron at a particular frequency, I can do it this way, and then the kinetic energy would be the maximum kinetic energy that I could have. And of course, that is for the least bound electron. So the ones that are held in with the least amount of force, they're going to have the maximum kinetic energy. So there's nothing to change with the equation. It's just simply noticing that the ones that are the easiest to kick out will have the maximum kinetic energy. Many electrons will require more energy than that bare minimum. So yes, using that WO here, W naught, technically you use it when we know that it is for the least bound electrons, or when I'm figuring out information about the least bound electrons. So that's technically when I assign it WO or W naught. So many electrons require more than that, and thus the kinetic energy of such electrons will be less than that maximum amount. From these considerations, the photon theory makes the following predictions on the next page. So here, an increase in intensity of the light beam, or the brightness, simply means I get more photons being ejected. So if I increase the brightness, that just simply means more packets of energy. So more electrons will be ejected, but since the energy of each photon is not changed, the maximum kinetic energy of electrons is not changed by increased intensity. So increasing brightness does not increase the energy, it just simply increases the number of photons. And that's what you saw in that simulation when you did it. When you adjusted the brightness at a particular frequency, it just simply meant more photons. And if the frequency of light is increased, or of course what that also means, when you did the when you did the simulation, that of course corresponds to lower lambda. So lower wavelengths means higher frequency. So they're inversely related, of course. So we were thinking of it in terms of wavelength, but technically the vice versa of that is frequency. The maximum kinetic energy of the electrons increased linearly according to the earlier equation is that. So all I did there was just simply, you had the original equation, so E equals HF is equal to KE max plus the amount of energy required to dislodge an electron. And of course, if I want to solve for KE, subtract WO, subtract WO. So of course the equation now becomes KE max, that's going to cancel, and we're left with HF minus W naught, or WO. And of course the relationships here in the top right. Now the next little simulation you're going to do is actually a little lab in which you're going to figure out you're going to figure out oh my goodness, you're going to figure out Planck's constant, because if I take a look here, this is really the same thing as a straight line. So we'll be taking a look at that and seeing that, oh, this is very similar to y equals mx plus b. And of course, if we set that to 0, then the slope is equal to delta, or equal to h. So if we know the kinetic energy max and at various frequencies, we can figure out that. But we'll leave that to the next video. So the relationship is up there. If the frequency is less than the cutoff frequency, where that gives me the lowest amount of energy required to make an electron jump. No electrons will be ejected. So I need to have that minimum amount to release, and that's going to, of course, mean a minimum frequency. And if I have less than that cutoff frequency, or the frequency required to make an electron be ejected, nothing's going to happen, no matter what the intensity of the light is. So these predictions of the photon theory are very different than the predictions of the wave theory. Careful experiments carried out by R.A. Millikan, the results were fully in agreement with the photon theory. All right. So these, one other aspect of the photoelectric effect also confirmed the photon theory. If extremely low light intensity is used, the wave theory predicts a time delay before electron emission so that the electron can absorb enough energy to exceed the work function. The photon theory predicts no delay. It only takes one photon, if its frequency is high enough, to eject an electron. And experiments show no delay, so that also confirms this theory. So calculate the energy of a photon of blue light. So we'll do an example here. We're looking for energy of blue light. So of course we have lambda equals 450 nanometers. And depending upon how we want to do this, so E equals HF. And of course from earlier using the universal wave equation, and if we're using it for the speed of light, it becomes this. And of course, F can be isolated here by dividing each side by lambda. And F is C over lambda. So I can substitute that into the equation here. So E equals HC over lambda. So of course I know what Planck's constant is, I know what the speed of light is. Wavelength though, it'll have to be in meters. So it has to be in meters, which means I have to convert this into meters. So of course from before, 1 times 10 to the 9 nanometers is equivalent to 1 meter. So that is how we can convert, or if you want to go back to our metric conversion sheet, a movement of 9. And since we're moving up the ladder, that would be to the left. So 4.5 times 10 to the minus 7 meters sticks. Okay, and then we have lambda. We have everything we need, so we can figure out the energy of blue light. HC over lambda. And of course, this is 6.63 times 10 to the minus 34 joules seconds multiplied by the speed of light. 10 to the 8 meters per second, all over 4.5 times 10 to the minus 7 meters. And of course what happens here, meters on the bottom and meters on the top cancel. Meters on the top of the numerator cancels with seconds on the bottom of the numerator, so we are going to be left with joules. That works out to be 4.4 times 10 to the minus 19 joules. So we can assume that we calculate the energy in joules rather than electron volts, unless it's otherwise stated in the question. All right, let's look at another example. Now we could do this a long way or we could do it a short way. I think I'm going to do it the shortcut way, because that way we won't have to convert anything. Because if you notice here, we're given the work function in electron volts. So what is the kinetic energy of an electron ejected from a sodium surface whose work function is 2.28 electron volts? So unless we were told differently, we can assume that we need that in electron volts, which means that we can use this other relationship that we have. So instead of energy in terms of joules, we have energy in terms of electron volts. So E, and we look at 1.24 times 10 to the 3, or just simply 1240, divided by lambda. And of course this is going to be in electron volts multiplied by nanometers, and wavelength is in nanometers. So of course what happens there is that nanometers and nanometers cancel, and we're left with electron volts. So we can just do that directly over here. So let's see here. So we're looking for kinetic energy, so eventually we're going to be using this E equals HF, which equals KE plus the work function. So we're looking at the kinetic energy, and of course we're not told if this is the work function, so that is the minimum amount of energy to release an electron. So that's going to technically give us KE max for each of these wavelengths. Okay, and of course, so to do that, of course, I need to have my energy value over here and rearrange and solve for KE. I know what this is, so I just need to figure out what the energy is. And I do that by figuring out this. So E is equal to 1240 over lambda. And in my first case, oh, this is so easy. I can just put it in directly. Put it in directly, and that'll give me my answer in electron volts. And we take 1240 divided by 310 or 410, I think that gives me 3.02 electron volts. So that's what E is going to be. So E is equal to, now notice sometimes I call it E equals this or HF equals that. It's the same thing. It's the same thing. So I have my 3.02. And the minimum energy is, so to get this electron out, it takes 2.28. So subtract 2.28, subtract 2.28, and in this case it's going to work out to be 3.02 minus that gives me, I believe, 0.74 electron volts. All right, so 0.74 electron volts is the energy that that thing will have. So again, we're imagining that that photon comes and hits that piece of metal and the electron goes flying out. We need to have 2.28 electron volts used to dislodge it, and the remaining amount of energy is simply used to move that on. Okay, I'm going to stop the video now, but what I'd like you to do is to, okay, well, what about at 550 nanometers? It has the same work function. The electron requires the same amount of energy to be dislodged, but when I'm using light of this wavelength, how much kinetic energy do I have? So you work through that and then tune into the third video.